scratching your head trying to figure out how massive online systems like, your favorite streaming service or global e-commerce site actually keep running so seamlessly. Or if you're maybe an aspiring senior software engineer looking to really elevate your game and land those sought-after roles at major tech companies, then you're absolutely in the right place.
Yeah, those interviews can be tough.
They really can. So our mission today is to take a deep dive into the, 30 essential concepts of system design. These aren't just theoretical ideas. They're like the fundamental building blocks that let modern distributed systems be scalable, resilient, and incredibly performant.
Right. Mastering them, like our sources say, it's a cornerstone for those senior engineering roles. It's what helps you understand the why behind the tech.
Exactly. Okay, let's unpack this. Today, we're diving deep into the very DNA of modern software, system design.
It really is about understanding the architecture beneath the surface, isn't it? Moving beyond just using the technology to grasping how it's actually designed to function under, immense pressure. And maybe more importantly, why certain design choices get made.
Precisely. And, to understand any complex system, you really have to start with the basics, right? The foundational communication layer. We're talking about the client-server architecture.
The absolute starting point.
Yeah. This is where almost every web application begins. So, in essence, a client could be your web browser, your phone app, whatever you're using it, sends a request. And a server processes it and sends a response back. It's like the handshake that underpins the entire internet, basically.
And what's fascinating there is this sort of hidden dance that happens just for that initial connection.
Yeah.
For clients and servers to even start communicating, they need to find each other first.
Right. How does that work?
Well, that's where IP addresses and DNS come in. You can think of an IP address as like a server's unique street address online, a specific identifier for that computer.
Okay. Like a phone number.
Exactly like a phone number for the server. But since nobody wants to remember, long strings of numbers like 192.168.1.1.
Definitely not.
We use human-friendly domain names like algomaster.io. So domain name system, or DNS, acts like the internet's giant phone book. It maps those easy names to their corresponding IP addresses.
I see.
So when you type in a website, your computer asks a DNS server, hey, what's the IP for this name? Gets the number back, and then uses that IP to connect directly. You can actually try this yourself with the ping command in your terminal, see the IP for any domain. It's kind of neat.
Huh, okay. So once they've found each other using DNS and IP, they need a common language to actually speak.
Precisely. That's where protocols come in. The main language clients and servers use is HTTP, the Hypertext Transfer Protocol. It's basically a set of rules for, transferring data back and forth.
But I always see HTTPS now.
Right. And that's crucial because vanilla HTTP has a major security flaw.
Yeah.
It sends everything in plain text. Anyone snooping on the network could potentially read it.
Yikes. Oh, okay.
Yeah. That's why virtually all modern sites use HTTPS. The S stands for secure. It means HTTPS encrypts all the data using protocols called SSL or TLS. This encryption scrambles the data, preventing anyone from eavesdropping or messing with it. Super important for things like logins or credit card details.
Makes sense. And often it's not just a simple client-to-server chat, right? Especially in bigger apps, there's sometimes another layer managing things.
Absolutely. That's where application programming interfaces or APIs become really critical. Think of APIs as standardized contracts, like a menu at a restaurant, that let different software parts talk to each other in a structured way.
Okay.
They act as a kind of sophisticated middleman. They define the requests a client can make, what format the data will be in, the rules of engagement. So a client sends a request to the API figures out what needs to happen, maybe talk to a database, call another service, and then sends back a nice structured response, usually in formats like JSON or XML.
Got it. So APIs manage the conversation.
Exactly. And one of the most common styles you'll hear about is REST, or representational state transfer. REST APIs are what we call stateless.
Stateless.
Meaning each request from the client has to contain all the information the server needs to understand and fulfill it. The server doesn't remember anything about the client from previous requests.
Oh, okay.
This makes them really simple, scalable, because any server can handle any request, and also easy to cache. REST treats everything as a resource, like a user or an order, and uses standard HTTP methods: get to fetch data, post to create it, put to update, delete to remove. Very common, very effective.
And then there's GraphQL. I've heard that mentioned too.
Right, GraphQL, it came out of Facebook. It offers a different approach. Instead of having fixed endpoints that return a set structure of data, like REST often does. GraphQL lets the client ask for exactly the data fields it needs, nothing more, nothing less. You can even combine requests for data from multiple resources into a single query.
Oh, that sounds efficient.
It can be, especially for complex front ends. It avoids getting too much data you don't need or having to make multiple separate requests. The trade-off, though, is that it generally requires more complex processing on the server side, and it's not as easily cached by intermediate systems as REST usually is.
Interesting. So, okay, what does this all mean for us then? Once our systems can actually talk to each other, the very next challenge, especially for any application that starts getting popular, is, well, how do you make sure it can handle more? More users, more data, just more of everything.
Yeah, that's the million-dollar question.
This is where the whole art of scalability really comes into play, isn't it?
Absolutely. Scalability, fundamentally, is just a system's ability to handle an increasing amount of work or users without, falling over or slowing down to a crawl.
Right, without performance taking a hit.
Exactly. And when we talk about making a system bigger, there's sort of two main ways to go about it. First, there's vertical scaling. People sometimes call it scaling up.
Scaling up.
Yeah, it just means upgrading a single server. You give it more powerful hardware, a faster CPU, more RAM, bigger disks. It can be a quick fix, especially when you're starting out.
Seems simple enough.
It is, initially, but it hits hard limits pretty fast. There's only so powerful you can make one machine, right? And the cost for those high-end servers goes up exponentially. Plus, and this is critical, it creates a single point of failure if that one super server goes down.
Your whole application is offline. Ouch.
Exactly. Not ideal for anything serious. Which leads us to the more robust approach, especially for distributed systems, horizontal scaling, or scaling out.
Okay, scaling out, how's that different?
Instead of making one server bigger and bigger, you just add more servers. You distribute the workload across multiple machines.
Wow, okay, like a team effort.
Precisely. This inherently gives you more capacity, and it dramatically improves reliability. Because if one server fails, the others are still there and can just pick up the slack.
That makes a lot more sense for bigger systems. But how do requests know which server to go to?
Great question. That's where a load balancer becomes absolutely essential. It's a piece of hardware or software that sits in front of your group of backend servers.
The traffic cop you mentioned earlier.
Exactly. It acts as a smart traffic manager. It takes incoming client requests and distributes them across your healthy servers using different strategies, different algorithms.
Like what?
Well, common ones are round robin, where it just sends requests to each server in turn, or at least connections, where it sends the new request to the server that currently has the fewest active connections. That's good if some requests take longer than others. There's also IP hashing, which tries to send requests from the same user, based on IP, to the same server, which can be useful sometimes.
Okay.
And crucially, the load balancer is always checking the health of the servers. If one stops responding, it immediately stops sending traffic there and redirects it to the healthy one, so it ensures continuous service.
Got it. So we've scaled the application servers. They can talk, handle more requests.
But what about the data itself? That's got to live somewhere, and those databases need to scale too, right? They're like the backbone.
Totally. Databases are fundamental, and broadly, we tend to categorize them into two main camps: SQL and NoSQL.
Right. SQL sounds familiar, like traditional databases.
Yeah, exactly. Think PostgreSQL, MySQL. SQL databases are known for their structured nature. They have rigid, predefined schemas. You define your tables and columns up front, and they strictly follow what are called ACD properties.
ACD, what's that?
It stands for atomicity, consistency, isolation, durability. It's a set of guarantees that ensure database transactions are reliable. For example, atomicity means a transaction, like transferring money, either completes entirely, all steps succeed, or it fails completely and rolls back. Nothing gets left half done.
Crucial for things like banking.
Absolutely. That strong consistency and structure makes SQL databases ideal for applications where data integrity and relationships are critical, like financial systems, inventory management, things like that. Okay. And NoSQL. That sounds like, well, not SQL.
Pretty much. NoSQL databases like MongoDB or Cassandra were really designed for the challenges of high scalability and performance in distributed systems. They typically don't enforce a fixed schema.
More flexible then.
Much more flexible. You can store data without defining the structure rigidly beforehand. They also support various data models, key value stores, document databases, graph databases, column family stores, each optimized for different kinds of data and access patterns. They're generally built for handling huge amounts of data distributed across many servers.
So when would you use which?
It depends, and actually, many modern applications use both. Maybe SQL for the core user account and transaction data where consistency is key, and NoSQL for things like user sessions, activity feeds, or product catalogs where flexibility and massive scale are more important. It's about picking the right tool for the job.
Makes sense. So how do you actually scale these databases when they get huge? Just add more servers like with the application?
It's a bit more complex with databases, but yes, distributing the load is key. We use several techniques. One common one is indexing.
Indexing, like in the back of a book.
Exactly like that. An index helps the database find specific data much faster without scanning the entire table. It dramatically speeds up read queries. The trade-off is that it can slightly slow down write operations, adding or updating data, because the index itself also needs to be updated.
Okay.
What else? Then there's replication. This means creating copies of your database on multiple servers. Usually you have a primary or master database that handles all the writes, and then one or more read replicas that handle the read requests. This is great for scaling read-heavy workloads and also improves availability. If the primary database fails, one of the replicas can be promoted to become the new primary.
Okay. So that handles more reads and gives you backup. But what if the data itself is just too massive for one server, even with replicas?
That's when you need sharding, also called horizontal partitioning. This is a technique where you actually split a single large database into smaller, independent, more manageable pieces called shards.
Splitting the data up.
Exactly. Each shard holds a subset of the data and typically lives on its own server. So instead of one giant database, you might have, say, 10 smaller ones. This distributes the data and the load, dramatically speeding up both reads and writes for enormous data sets.
Sounds powerful. Any downsides?
Oh yeah. Sharding is incredibly powerful for scale, but it introduces significant complexity. You have to figure out how to split the data, the shard key, how to route queries to the right shard, how to handle transactions that might span multiple shards, and how to rebalance data if one shard gets too full. It's a major engineering challenge.
Right. Not something you do lightly.
Definitely not. There's also vertical partitioning. Instead of splitting rows like sharding does, this splits a table by columns. If you have a table with many columns, but queries usually only need a few of them, you could split it into multiple tables, each with fewer columns. This can improve query performance because the database only needs to scan the relevant columns.
Okay, splitting by columns instead of rows.
Yep. And one more technique to mention is denormalization. This one feels a bit counterintuitive if you come from a traditional database background.
How so?
Well, traditional database design aims for normalization, eliminating data redundancy. Denormalization does the opposite. You intentionally add redundant copies of data or combine related data into a single table, even if it means duplication.
Why would you want duplication?
To speed up reads. By having related data together in one place, you can avoid expensive join operations where the database has to combine data from multiple tables. Fewer joins often means much faster queries.
I see. Trading storage space for speed.
Exactly. It makes reads faster and simplifies some queries, but it increases storage costs and makes updates more complex, because now you might have to update the same piece of data in multiple places and keep them consistent. It's a trade-off.
So many trade-offs. Okay, so we've scaled servers, databases. But what about the application code itself? If it's just one giant program, doesn't that become hard to manage and scale specific parts?
You've hit on a major trend in modern architecture, microservices.
Microservices, right. Heard a lot about those.
The idea is to break down a large monolithic application, one big code base, into a collection of smaller independent services. Each service focuses on a single, well-defined business capability.
Like one service for user accounts, another for payments, another for product search.
Exactly like that. Each microservice typically has its own dedicated database, its own internal logic. And the really powerful thing is that these services can be developed, tested, deployed, and importantly, scaled completely independently of each other.
So if your payment service gets hammered, you can just scale that service up without touching the others.
Precisely. You scale only what needs scaling. It allows teams to work more autonomously and deploy changes faster and more safely.
But how do all these independent services talk to each other reliably, especially if one is slow or temporarily down?
That's where message queues often come in. They enable asynchronous communication between services. They act like a buffer or a mailbox.
Asynchronous meaning not immediate.
Right. Instead of one service directly calling another and waiting for a response, which is synchronous and can cause blockage if the called service is slow, a producer service just puts a message like, order placed into a queue.
Okay, like dropping a letter in a mailbox.
Exactly. The queue holds the message safely. Then later, when a consumer service, like an order processing service, is ready, it picks up the message from the queue and processes it. This decouples the services. The producer doesn't have to wait for the consumer.
I see. So if the order processor is busy, the messages just pile up safely in the queue until it catches up.
Yep. It prevents a slow service from bringing down the whole system. It makes the overall architecture much more flexible, resilient, and scalable, especially for event-driven systems where a lot of things are happening concurrently.
That's a really big shift from how things used to be built. Okay, so now we know how systems talk, how they grow. Let's talk about how they stay strong. How do we design them to handle failures gracefully? Because things do go wrong, right?
Absolutely. Failures are inevitable in distributed systems. Networks glitch, servers crash, disks fail. Resilience is key.
And we've actually already touched on some concepts that directly help with this, haven't we? Like horizontal scaling, just having multiple servers means if one fails, others can take over.
Definitely. That inherent redundancy is a huge win for reliability.
And load balancers are critical too, because they actively detect those unhealthy servers and stop sending traffic to them.
Exactly. They provide that automatic failover capability.
And replication for databases having copies means if the primary fails, a replica can step up, minimizing data loss and downtime.
Right. Those are all fundamental building blocks for resilience. But there's a really core principle in distributed systems that forces us to think hard about trade-offs during failures. The CAP theorem.
Ah, yes, CAP. Consistency, availability, partition tolerance. Heard of it, but can you break it down?
Sure. The CAP theorem basically states that in a distributed system, any system involving multiple computers communicating over a network, it's impossible to simultaneously guarantee all three of these properties.
Okay.
Consistency. Every read receives the most recent write or an error. Essentially, everyone sees the same data at the same time.
Every request receives a non-error response, without guarantee that it contains the most recent write. The system keeps working.
The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. Basically, it handles network failures.
So you can't have all three?
Nope. And here's the kicker. Network partitions failures, where parts of the system can't talk to each other, are basically inevitable in any large-scale distributed system. You have to design for partition tolerance.
Okay, so P is mandatory.
Pretty much. Which means you're forced to choose between the other two. Consistency, C, or availability, A. Do you want the system to always return the absolute latest data, even if it means sometimes it has to return an error or be unavailable during a network partition? Choosing C over A. Or do you want the system to always respond, even if it means sometimes returning slightly older, stale data during a partition? Choosing A over C.
Wow, okay, that's a fundamental choice. Like the triangle analogy, you pick two corners, and since P is a must, it's either CP or AP.
Exactly. That decision profoundly impacts how the system behaves during failures and guides many other design choices.
So besides handling partitions, what else makes a system robust when, say, requests get duplicated?
That's where idempotency becomes super important.
Idempotency, what does that mean?
It means that making the same request multiple times produces the same result as making it just once. The system detects or handles the duplicate request so it doesn't cause unintended side effects.
Can you give an example?
The classic one is online payments. Imagine you click Pay Now, but your network lags, so you click it again. If the payment operation isn't idempotent, you might get charged twice.
Oh, definitely don't want that.
Right. An idempotent system would recognize the second request, maybe based on a unique transaction ID, and ensure the payment only goes through once. It's crucial for reliability anywhere that requests might be retried automatically by the network or accidentally by a user.
Makes sense. And for microservices, you mentioned the API gateway earlier. How did that help with resilience?
The API gateway acts as that single front door for all incoming client requests to your microservices backend. It does the routing, but it also handles a lot of cross-cutting concerns.
Like what?
Things like authentication, making sure the user is who they say they are, rate limiting, preventing abuse, which we'll get to, logging, sometimes even basic request transformation. By centralizing these, it provides a protective layer. Individual microservices don't have to worry about implementing all that stuff themselves. It simplifies the services and makes the whole system more robust and manageable.
So it's like a bouncer and a receptionist rolled into one.
Kind of, yeah. It controls access and directs traffic appropriately, while also handling some common tasks. This really raises that important question for designers. How do we build systems that aren't just fast, but, incredibly robust, ready for when things inevitably break.
That really is the core challenge. Okay, speaking of fast, let's pivot to performance. How do we make systems deliver results quickly and efficiently? One obvious factor seems like distance, right? Reducing latency.
Absolutely. Latency is basically delay. A big part of it is often just the physical distance data has to travel over networks. Light speed is fast, but not infinite.
So if my server's in New York and my user is in India.
Exactly. The request has to travel halfway across the world and back. That round-trip time adds noticeable delay. The primary solution here is to bring the servers closer to the users. Deploy your services across multiple data centers globally.
So users connect to the nearest one.
Precisely. Connecting to a server in, say, Mumbai instead of New York drastically cuts down that physical travel time and latency.
Okay, besides geography, what are the big performance boosters? I hear caching mentioned all the time.
Caching is huge. It's probably one of the most effective ways to speed things up. The core idea is simple. Store frequently accessed data in a much faster place, usually in memory, so you don't have to keep fetching it from the slower main database or doing expensive computations.
So keep copies of popular stuff handy.
Exactly. A very common pattern is called cache aside. The application first checks the cache for the data it needs. If it's there, a cache hit, great, return it super fast. If it's not there, a cache miss, then the application fetches it from the database, stores a copy in the cache for next time, and then returns it to the client.
But what if the data in the database changes? The cache would be stale.
Good point. That's why cache entries usually have a time to live, or TTL value. It tells the cache how long to keep the data before considering it expired. Once it expires, the next request will trigger a fetch from the database, refreshing the cache with the latest version. Choosing the right TTL is a balancing act between performance and data freshness.
Got it. And what about delivering website content itself, like images and videos?
For static assets like HTML files, JavaScript, CSS, images, videos, especially delivering them globally, we use content delivery networks, or CDNs.
CDNs. How do they work?
A CDN is basically a large geographically distributed network of servers. They store copies of your website's static content in locations all around the world, close to where your users actually are.
So like caching, but for website files and distributed globally.
Exactly. When a user requests, say, an image from your site, the request is automatically routed to the nearest CDN server, edge server. That server delivers the image directly instead of the request having to go all the way back to your main origin server. This results in much faster load times, less buffering for videos, and it also reduces the load on your main servers.
That's why streaming videos usually start so quickly.
CDNs are essential for that, yeah.
Okay, but what about really large files, like maybe raw video uploads, backups, big PDF documents, stuff that isn't really structured data for a database, but needs to be stored somewhere scalable?
Right, you wouldn't want to cram huge binary files directly into your main operational database usually. For that kind of large unstructured data, we use blob storage.
Blob
stands for binary large object. Think services like Amazon S3 or Azure Blob Storage. They are specifically designed to store massive amounts of file-like data cost-effectively and durably. You typically organize blobs into logical containers, often called buckets.
So it's like a massive scalable file system in the cloud.
Kind of, yeah.
Yeah.
But optimized for durability, availability, and access, typically via simple HTTP APIs using unique URLs for each blob. It offers huge scalability, pay-as-you-go pricing, and it's separate from your compute and database resources. Perfect for images, videos, logs, backups, you name it.
Fascinating how many specialized tools there are.
Yeah.
Okay, let's shift gears slightly. How do we move beyond that standard HTTP request response cycle for things that need truly real-time updates, like a live chat application or a stock market ticker?
Great question. The standard HTTP model is pull-based. The client asks, the server responds. For real-time, you often need the server to push data to the client proactively. That's where WebSockets come in.
WebSockets. How are they different?
Unlike HTTP, which usually involves opening a new connection for each request-response pair, or reusing connections inefficiently, a WebSocket connection, once established, stays open. It provides a persistent, bidirectional communication channel between the client and the server.
Bidirectional. Both ways.
Yep. The client can send messages to the server, and the server can push messages down to the client at any time without the client having to constantly ask, anything new, anything new. This eliminates the need for inefficient techniques like polling and enables genuine real-time experiences.
So that's how chat messages appear instantly.
That's a very common use case, yes. Live dashboards, collaborative editing, multiplayer games, lots of applications benefit from WebSockets.
Okay. What about webhooks? I hear that term too. Are they similar?
Webhooks are also about real-time notifications, but they're typically used for server-to-server communication, not usually client-server like WebSockets.
Ah, okay. How do they work?
Instead of one server constantly polling another server asking, did that event happen yet? A webhook allows the first server to register a URL with the second server. Then, when the specific event does occur on the second server, like a payment completed or a new user signed up, it instantly sends an HTTP PUST request containing details about the event to the registered URL on the first server.
So it's like the server getting a notification pushed to it when something happens elsewhere.
Exactly. It's event-driven and much more efficient than constant polling, saving resources on both sides.
Makes sense. One last performance stability thing. Rate limiting. Why is that important?
Rate limiting is crucial for protecting your services. It restricts the number of requests a client or maybe an API key can make to your server within a specific time window, like, say, 100 requests per minute.
Why restrict them?
To prevent abuse, either from malicious bots trying to overwhelm your service, a denial of service attack, or even just from a legitimate but poorly behaved client making way too many requests and hogging resources, degrading performance for everyone else. If a client exceeds the limit, their subsequent requests might be blocked or slowed down for a period.
And you mentioned the API gateway can handle this.
Yes. It's a very common place to implement rate limiting right at the entry point to your system. It keeps your backend services from getting flooded.
Right. So here's where it gets really interesting, right? Seeing how all these tools, WebSockets, webhooks, caching, CDNs, move beyond simple request response to create these really dynamic, responsive, and stable experiences. It sounds like a complex orchestra.
It really is. And conducting that orchestra well, that's system design.
Which brings us perfectly to the final crucial part. Every single one of these design choices, these tools we've discussed, involves balancing trade-offs. There's rarely a single best answer, is there? This feels like the true art of system design.
Absolutely. It's never black and white. You're constantly evaluating these compromises based on your specific needs, performance versus cost, consistency versus availability, simplicity versus scalability. Understanding and navigating these trade-offs is what separates a functional design from a truly great one.
So let's quickly recap some of the key ones we've hit on, like security and communication.
Right. Choosing HTTPS gives you that vital data privacy and integrity through encryption, the trade-off. A small but measurable overhead in computation for encrypting and decrypting everything compared to plain, insecure HTTP. Usually a trade-off well worth making for anything sensitive.
And API design REST versus GraphQL.
Yep. REST is generally simpler, very cacheable, great for public APIs with predictable usage. But it can lead to overfetching or underfetching data. GraphQL offers that fantastic flexibility for clients to get exactly what they need, potentially reducing network traffic, but it comes with more server-side complexity and challenges around caching. The choice really depends on your API consumers and data complexity.
And the big database choices, SQL versus NoSQL.
A classic trade-off. SQL gives you strong consistency, structured data, great for relational integrity like in finance. NoSQL offers massive scalability, flexibility with schemas, often higher availability, better suited for huge, rapidly changing data sets like social feeds. Again, it hinges on your data's nature and your consistency requirements. You might even use both in the same system.
Then scaling application servers. Vertical versus horizontal.
Vertical scaling, bigger servers, is simple initially, but hits limits and creates a single point of failure. Horizontal scaling, more servers, offers near limitless capacity and better reliability, but introduces the complexity of managing distributed systems and needing things like load balancers. It's about initial simplicity versus long-term robustness and scale.
And even within database scaling, those techniques had trade-offs.
They sure did. Let's quickly run through them.
Speeds up reads, but slightly slows down writes.
Scales reads and improves availability, but doesn't inherently scale write capacity. Writes usually still go to the primary.
Scales both reads and writes for massive datasets, but adds significant operational complexity.
Speeds up reads by avoiding joins, but increases storage needs and complicates data updates due to redundancy.
So you really need to know your application's read-write patterns.
You absolutely do. There's no magic bullet. It's about picking the right combination of techniques for your specific workload, data size, and tolerance for complexity.
And underpinning so many of these choices, especially around failure, is the CAP theorem.
Right. It's that fundamental constraint. Since network partitions are unavoidable, you must make a conscious decision. Prioritize strong consistency, C, or high availability, A, when those partitions happen. That choice guides so much of the system's architecture and behavior under stress.
The core takeaway seems to be, there's rarely one perfect solution. It's always context, requirements, and making informed compromises.
That's the essence of system design, really. Understanding the building blocks, knowing the trade-offs, and putting them together intelligently to meet the specific goals.
And there you have it, a whirlwind tour through maybe around 30 essential concepts in system design. We've gone from that basic client-server handshake all the way through advanced techniques for scaling, resilience, and performance. It's pretty clear that mastering system design it's definitely an art. It combines that deep technical knowledge with really strategic decision-making and the ability to, spot the challenges, evaluate these unavoidable trade-offs we just discussed, and then apply the right solutions. That's what truly defines a skilled system designer in today's incredibly complex tech landscape.
Absolutely. And maybe as a final thought for everyone listening, as you reflect on this deep dive, maybe pick a real-world application you use every single day. Could be social media, online banking, maybe a ride-sharing app, anything complex. Based on what we've talked about today, caching, databases, scaling, real-time stuff, the CAP theorem, which of these concepts do you think are absolutely most critical for that specific application to function the way it does? Is it prioritizing consistency above all else? Or is high availability the absolute must-have? Or maybe it's the sheer speed of real-time updates? And importantly, what trade-offs do you imagine the engineers behind it might have had to make to achieve that specific balance? Thinking about that can really help solidify these concepts.